Hi everyone, welcome to my presentation. I'm going to talk today about the structural and magnetic properties of platinum cobalt manganese multilayers. My name is Martin Lonsky and we have conducted this work at the Department of Material Science and Engineering at the University of Illinois at Urbana-Champaign. This work got recently published in Physical Review Materials, so if you're interested in more details on this topic, please feel free to take a look at this article. I want to begin my presentation with a short motivation and talk about skyrmions in magnetic multilayers. And for this purpose, let me first introduce the relevant exchange interaction terms. The first one being the symmetric exchange. We all know if we look at the Hamiltonian in the Heisenberg model, and we have two adjacent spins, Si and Sj, depending on the sign of this exchange constant, the spins like to be aligned in a parallel or anti-parallel way, so we end up having a ferro or an antiferro magnet. In the second case of the Dzieloszynski-Maria interaction, we have an antisymmetric exchange, which means that the two neighboring spins like to arrange themselves in a perpendicular way because of this cross product that is included in this term here. And now if we combine these two terms, we usually end up having magnetic configurations such as helical spirals, but under certain conditions, skyrmions can form, and these are small magnetic whorls, as you can see here in these examples. Initially, they have been observed in only very specific material systems at low temperatures, but it turned out that in magnetic multilayers, with their highly tunable properties, it is easier and more convenient to create and observe skyrmions even at room temperature. And one class of those magnetic multilayers are platinum cobalt based multilayers. So we all know platinum cobalt multilayers. And now if we add a third metallic layer, we sort of break the spatial inversion symmetry even further and can obtain a sizable Dzieloszynski-Maria interaction. But this really depends on the third metallic material that we have been using. And in this work, also published in Physical Review Materials, it has been shown that it really depends on the difference in the work function of cobalt and this third material here. So we have been thinking about using manganese because it hasn't been studied yet. And here we really have a reasonably large difference in the work functions of cobalt and manganese, and therefore one might expect the formation of skyrmions or other interesting observations in this material system. Here are just shown two examples of two different material systems. For example, Lorentz TEM measurements, how skyrmions can be observed and how they occur in an ordered or rather disordered fashion, and oftentimes it's also related to the formation of labyrinth-like domains, and then under the application of magnetic fields and current pulses, you can obtain magnetic skyrmions. The methods we have been using are magnetron sputtering for the fabrication of our multilayers, using these parameters mentioned here. We have carried out a structural characterization using X-ray reflectometry and also scanning transmission electron microscopy measurements. We have done magnetic characterization using an MPMS system by quantum design, which allowed us to perform squid measurements essentially. And we have also carried out magneto-optical measurements using Kerr microscopy. So let me start with the structural analysis here with X-ray reflectometry. And here you can see for 4 examples with different repeat numbers of the platinum cobalt manganese trilayer, so n equals 2, 4, 6, and 8. And you can see that the experimental data, which is shown in different colors, is always in an excellent agreement with the numerical fit that we have carried out. And therefore we can say that the multilayer quality is very good and exactly what we would expect. The maximum interfacial roughness is around 4 angstrom, so this is also very satisfying. And therefore, we can say that we have high quality multilayers, which is also shown in STEM measurements. You can see that these layers are nicely separated that we have all the chemical elements that we would expect at the respective positions, and therefore we have a good solid basis for the magnetic characterization. And this I will show now on the following slides. So first of all, we have measured the hysteresis loops at room temperature, applying an out-of-plane magnetic field, and this is now shown for different repeat numbers again of the platinum cobalt manganese trilayer. And you can see with an increasing repeat number, of course, the total magnetic moment gets larger, and also the hysteresis or the field range where the hysteresis loop occurs gets more broad, which is also expected. If you compare this to in-plane measurements, you get exactly what you expect for an out-of-plane anisotropy. So there is hardly any hysteresis observed here. And we also see an encouraging observation that the shape of those out-of-plane hysteresis loops looks very similar to other Skyrmion hosting magnetic films and multilayers. So this is one step towards the right direction, I would say. And when we look at the cobalt and manganese thickness dependence, so first of all, let's vary the manganese thickness for a repeat number of n equals 2. And you can see that if we increase the manganese thickness, the hysteresis shape changes, which is interesting. But also the total magnetic moment is being reduced, which is even more interesting, and we'll discuss that in a little bit. And for the cobalt thickness, maybe it's a little bit more straightforward. What happens is that for lower cobalt thickness values, we have a sharp switching here, which means that we have a strong out-of-plane anisotropy, and this kind of transitions into an in-plane anisotropy for larger cobalt thicknesses. Going back to the manganese thickness dependence, we also observe this for higher repeat numbers, for example, n equals 10. So this confirms what we have seen before and really shows that this is a universal observation here. So to get a better understanding of what is actually going on, we have also performed temperature-dependent hysteresis loop measurements. And we see a very interesting behavior in the coercive field as a function of temperature when we vary the manganese thickness here. So if there is no manganese present or only very thin layer, it hardly changes if we go towards, let's say, 20 Kelvin. But if we have a reasonably thick manganese layer here, you can see that the coercive field increases quite a bit. And this is a very unusual behavior and does not occur if we, for example, use tantalum instead of manganese. Then we again have this more or less flat curve. So the presence of manganese really changes something magnetically here. And this can also be seen here in a different way if we plot the manganese thickness for different magnetic fields here and the coercivity. On the y-axis, we can see that there is even a maximum at a certain manganese thickness at every temperature, basically, especially at low temperatures. Okay, and the reason for this is probably an antiferromagnetic coupling that is introduced by the manganese at the cobalt manganese interface, or even some kind of spin glass behavior that we observe here. Now, looking at the MOAK imaging, we also see an interesting dependence on the manganese thickness. So for thin manganese layers, we see some kind of a domain pattern, not very well ordered, but you can see the individual domains here in black and white. And these domains get actually smaller if we increase the manganese thickness here. And at higher manganese thicknesses, you can even observe something that looks like bubble-like domains or even magnetic skyrmions, which is also a very interesting observation, of course. If we vary the cobalt thickness, everything also changes in a very systematic way. Basically the overall domain pattern, but only as a function of the manganese thickness we get to something which may be magnetic skyrmions or at least bubble-like domains. An interesting behavior is also oftentimes we have seen that if you sweep the magnetic field and remain at a constant magnetic field thereafter, then the magnetic configuration will still change as a function of time. And this is visualized here by looking at this hysteresis loop. So we saturate the magnetic multilayer sample, then we sweep the field to a very small field value and simply wait for a long enough time. And you can see that we end up having this kind of S-shaped curve for the magnetic moment as a function of time. And this is in very good agreement with a work by Woodward et al. Done on platinum-cobalt multilayers. So now we are already at the summary of the presentation. You can see that we have observed a novel multilayer system, platinum-cobalt-manganese, and studied it systematically. We have seen that the structural properties are exactly as we would expect them to be, and the samples are of high quality. We have observed a systematic dependence on the cobalt and manganese thickness for the magnetic hysteresis loops that we have measured. The temperature dependence was very interesting and indicates the presence of antiferromagnetic coupling at the cobalt-manganese interface. And we even observed the presence of bubble-like domains or even possible Skyrmion states as demonstrated in our MOC measurements. And I've also briefly mentioned the slow domain dynamics at small fields, as it was also observed for platinum-cobalt multilayers. So with that, I would like to thank you for your attention, and I'd be happy to hear from you regarding any possible questions that you might have. Thank you.